Okay, hello everyone, and as I have already told you that the aberration chapter will take at least 4 to 5 videos. So this is the second part of the video, and in this part, I am going to cover paraxial assumption and spherical aberration. So what is paraxial assumption and what is spherical aberration? Then we will go to coma and other aberrations, and then we will go to Jernicke polynomials and other stuffs. Okay, so let's just start with the paraxial assumption. Paraxial assumption is most centrally important assumption that you have to understand. Otherwise, the basics of the aberration goes out of your hand. Okay, so paraxial assumption assumes that sin theta is theta when theta is radian. Okay, sin theta is theta or tan theta is theta. But you have to understand when theta is radian. What do you mean by that? The value of sin theta when theta is radian equals to theta. It doesn't matter sin theta or theta, but it has to be value of theta must be in radian, not in degrees. Okay, must be in radian. This assumption only accurate when following two conditions. It's not accurate in every scenario, and that's where aberrations comes. Okay, but it's accurate when a small angle of incidence with refractive surface, commonly referred as paraxial rays. Okay, if the incidence angle is smaller, and another is image is produced by spherical surface. Okay, image is produced by spherical surface, that's one story. Then another, which is main important clause that we have to understand, is a small angle of incidence. Angle of incidence must be small. Okay, so that's two condition where sin theta is equal to theta or tan theta is equal to theta happens when theta is radiant. This assumption becomes less accurate as the angle of incidence increases. As the angle of incidence increases, so better estimation is sin theta gives by the following expression. If theta is small, then this expression happen. It continues. Okay, so then this expression happens. Sin theta is equal to theta minus theta cube divided by 3 factorial plus theta to the power 5 divided by 5 factorial minus theta to the power 7 divided by 7 factorial. You know factorial, isn't it? 3 factorial means, so 3 factorials mean 1 into 2 into 3. Okay, 5 factorials means 1 into 2 into 3 into 4 into 5. In mathematics, this one of the speed progressing anything sign is factorial, not exponential. Exponential. Okay, so what I basically try to say is, to for paraxial assumption there must be spherical surface. Okay, let's take example. This surface has a radius here. Okay, spherical. And another point, this is optical axis. Another point is, if light comes closer to the optical axis, which is paraxial rays, don't you think? So in let's take example. If paraxial, if there is a spherical surface, then what is the normal here? Normal should be radius, isn't it? That's what we have been talking about in previous videos. So angle of incidence is this, isn't it? It's very small. If you move further away, let's take an example of this ray, which is not which is not paraxial, is it? It's a peripheral ray. Then what is the radius? What is the what do you call this? Normal here, extend from radius. The angle of incidence is way higher, isn't it? So what we have done in Snellen's law, sine theta 1 n1 is equal to sine theta 2 n2, isn't it? So it means n1 and n2 are constant always. They're somewhere 1 and 1.5 or whatever. When you increase theta 1, if you increase this angle, theta 2 must be increased, because sine is a function of sine 0 is equal to 0 and sine 90 is equal to 1. So it's always progression. When you increase theta 1, theta 2 must increase. And in this case, in case of refraction, must increase up to critical point, isn't it? Up to critical angle, isn't it? So it's a simple way to explain sine theta and cos theta. So if theta increases, then angle of refraction also increases, isn't it? From normal it comes towards the Focus is here. In this case, its focus is far, and the two focused are not at the same point, and that's what is that? That's aberration, isn't it? That's aberration. This aberration is sometimes called spherical aberration, but you have to understand paraxial approximation only applies if it is spherical and if angle of incidence is small. For angle of incidence is small, it must be paraxial ray, not abaxial ray, not peripheral rays, but paraxial rays. Paraxial rays means rays that are closer to optical axis, isn't it? So it's rays that are closer to optical axis, rays that are very close to optical axis and the vertex. That's called uh, paraxial rays. So you have to understand these two conditions. Otherwise, there will not be sin theta is theta when theta is radiant. It's not going to happen. It's going to happen only in paraxial approximation. For that, you need spherical surface. Second, you need paraxial rays because angle of incidence are so small. If theta is big, then there is no sin theta is equal to theta. Okay, this is not going to happen if theta is large. Okay, fine. So paraxial assumption, in if paraxial assumption breaks, this is the condition. Okay, then when third order approximation, that's only if we take this chunk, is used, image formation differ from what predicted by paraxial equation by 5 ways. And these 5 ways we usually call Seidel aberration or classical aberration. Okay, if sine theta is equal to theta is not happening, and then we take only one term extra, 3 factorial, then 5 types of aberrations come, and this 5 types of aberration is called Siedel's aberration or classical aberration. Okay, now today we are going to discuss on Siedel's aberration, especially first aberration, that is spherical aberration. Okay, classical optical aberration, there are two schools describe the classical aberration. The traditional old school, after German ophthalmologist Erich Seidel and the German physicist astronomers Karl Schwarzschild. The new school of classification named after optical physicist Fred Jernicke, 1953 Nobel Prize winner due to phase contrast microscopy. So you will see Jernicke polynomial a lot in aberrometry, especially now pentacam, um, other instrument like for example bone series pentacam and other instrument. You can easily analyze Jernicke polynomial. There are a lot of things, and in refractive surgery you will see a lot of Jernicke polynomials. So we will discuss later on in part 4, I think, or part 5, I think, Jernicke polynomial. But you have to understand first the classical old school aberration, which is Siedel's aberration. So in case of in 1850, Louis von Siedel described 5 monochromatic aberration. See, this is not chromatic aberration, this monochromatic aberration, which affects the image, which means monochromatic aberration means it happens in reflection also, not just refraction, in reflection also. Okay, it affects the image when object is far off axis or area of the lens is far enough from the axis, isn't it? Far off axis means it's not at closer paraxial rays, so that it means. Okay, so monochromatic aberration, also known as Siedel's aberration, 5 aberrations, is it? Spherical aberration, coma, oblique astigmatism, curvature of image, and distortion. So today we are discussing about spherical aberration, but I am seriously telling you guys, you have to understand paraxial approximation, which is very crucial. Okay, in case of optical aberration, there are two types of aberration we have discussed. Chromatic aberration. Chromatic aberration only in the lenses, as I have told you, not in mirrors. Monochromatic aberration, both lenses and mirrors. Okay. And monochromatic aberration, there is serial aberration and there is Jernicke polynomials. Jernicke polynomials. We don't tell Jernicke aberration. We call Jernicke polynomial. Okay. Serial aberration, it categorized into two topic. That is point aberration if point object is given point image is not formed. That kind of aberration is point aberration. Field aberration, it needs larger field to have aberration. So it's central importance. Okay, point aberration is spherical aberration, coma, and oblique astigmatism, or sometimes called astigmatism. Field aberration is curvature of the image and distortion. Okay, it happens only in the large field, not in the point. Okay, so Jernicke polynomials is lower order and higher order. Lower order is defocus and astigmatism. Definitely lower order, there are piston and tilting of the image. But they are not clinically significant. So clinically significant is second order, which is definitely defocus and astigmatism. But higher order is very important when we are going to talk about refractive surgery, diagnosis of keratoconus, diagnosis of PMD, and all these things. So in that case, spherical aberration, coma, higher order astigmatism, they are all in higher order astigmatism. After third order astigmatism, all are higher order astigmatism, and we're going to discuss about Jernicke polynomial in detail. Don't worry about it. Okay, let's move forward. Serial separation, see, it's very important. Serial aberrations depend upon the lens diameter, definitely, object size, definitely, lens position. Okay, it independent of the wavelength of monochromatic light. It doesn't matter. It's whether it's 400, whether it's 700. It is going to happen there. It doesn't matter. Theoretically, to avoid the aberration, required to correct all previous aberration. So theoretically, to avoid aberration, we need to correct all previous aberration, but let's not think about it now. So let's come to the term spherical aberration. Okay, what is spherical aberration? The world becomes aware of the spherical aberration. The world began aware of the spherical aberration due to the early problems related to image obtained by Hubble Space Telescope. So it's just a history. So I'll show you figure after. See, it is on-axis aberration. It means what? It means if it is an optical, it's not object is not here, which is off-axis. Object is close to optical axis. It's on-axis aberration. Okay, it's off-axis aberration. It's coma. When object is not at the axis, it's central important. It's not at the optical axis. It's central important. Okay, remember that thing. Okay, and light is striking the periphery of the lenses, non-paraxial lens, isn't it, are focused closer or nearer to the lens than those striking at the central paraxial rays. Isn't it that picture I have already drawn here? Light striking in the periphery, that is not paraxial, peripheral, focuses on this closer to the lens, isn't it? Focuses closer to the lens. Then light is striking on the center, closer to the optical center, which is paraxial rays, always focuses behind the lens. And this is the picture also tells you that spherical aberration. Okay, the problem mainly large aperture optical systems. See, so it is not a problem with our eyes because our eyes has pupil which constrict the aperture size. So that's not a problem with our eyes. So it affects sharpness of the image, not a position of the image. It affects only sharpness of the image. Central important. So uh, in case of longitudinal or spherical aberration, the distance long in the optical signal between peripheral rays and peripheral rays. See, let me draw. This is the picture. If peripheral light hits, it focuses closer to the lens, and if paraxial rays hits, it focuses far from the lens, and this gap is spherical aberration. So it's simple as that. Okay, so in this picture, spherical aberration manifests the difference focal point of paraxial and peripheral rays, and we noted the image eventually evenly distributed soft focus, so it's getting blurred, isn't it? So this is what I am talking about. The first Hubble telescope, this is the picture before correcting spherical aberration. Okay, and after correcting spherical aberration, see the picture how clear it is, isn't it? So pause the video and you can read that figure 8.13 and all these things. Okay, I have taken this picture from the Professor Dr. George Esimeli's book. Okay, so spherical aberration, there is two type of spherical aberration: positive spherical aberration and negative spherical aberration. It's really simple to understand. Positive spherical aberration means if it is light, Peripheral light focuses front and central light, which is basically light that is paraxial rays focuses and distance, isn't it? Peripheral rays have shorter focal length. This focal length is shorter, and central is focal length is larger. It's positive, and negative means exactly opposite. Central rays have shorter focal length than the peripheral rays. Okay, so this is the picture. This is actually a picture of basically positive spherical aberration. Just don't confuse with this negative lens. Negative lens means this periphery has shorter focal length and this center has longer focal length, isn't it? Just don't get confused with this minus lens. Okay, spherical aberration versus shape factor. See, if you change the shape of the lens, spherical aberration changes. See, this is the maximum spherical aberration. If the plano convex lens, plano side is shown towards the light, but least if plano side is opposite towards the light, towards the eye, and this is the meniscus shape. Can you see? That's why we use in our setup, in our basic daily life, that our spectacle that we have used is always in meniscus shape. This is one of the answer, not all the answer, but one of the answer. In case of meniscus shape, aberration, spherical aberration basically reduces. Okay, so can you see this thing? Only flipping the lens means spherical aberration goes from this to this. It's so important that lens design is central important to controlling spherical aberration. So negative spherical aberration is possible with spherical lens. It's not at all. So non-spherical lens, peripheral lens is uh, always bent towards the center. Okay, this is positive spherical aberration and this is negative spherical aberration. So paraxial rays focus closer than the non-paraxial rays. It's always that in case of spherical lens, it is not possible to have negative spherical aberration. So other clinical applications for spherical aberration is very important. A lot of people don't know about it. Accommodated eyes typically, but not always, manifest positive spherical aberration, which tends to increase with age. So in case of unaccommodated eye, positive spherical aberration increases. Spherical aberration would be even greater if not for the spherical nature of the cornea. The periphery of the cornea is flatter than the center. So why our nature selects cornea as prolate? Because if cornea is prolate, then eyes spherical, positive spherical aberration decreases. That's why nature chooses cornea as a prolate. If cornea is fair, then it will be devastating for our image, because if cornea becomes sphere, then positive spherical aberration increases so high it will create blur in our retina. But it's not that. Cornea is not spherical, it's prolate, because center is steeper and periphery is flatter. That's why positive spherical aberration reduces, not zero, but definitely reduces. As I accommodate, amount of positive spherical aberration decreases. It's central important to understand when we accommodate, so spherical aberration decreases. And night myopia, see, when we are talking about night myopia, there are multiple factors. See, one factor is empty field accommodation, which happens with the pilot or astronauts. And another factor is under dim light condition, pupil dilates and exposes retina non-paraxial rays. And when non-paraxial rays formation, peripheral rays focuses in front of the eye. That's why this light ray focuses in front of the retina and makes creates myopia. This is one condition for myopic night myopia. This is one condition for night myopia, which is spherical aberration. Okay. So another condition is in empty space accommodation. So that's why sometimes I prescribe my patient who said night driving and all 0.5 more uh, minus sometimes. So spherical aberration depends on lens aperture and diameter, lens shape, definitely incident beam configuration, refractive index. Spherical aberration is minimized with a proper combination of lens shape factor and beam geometry. I have already discussed about it. It can also be compensated by the lens combination. The spherical lenses are specifically designed for minimizing So you can see this whenever you see in clinic. Just watch 90 diopter, 78 diopter, 20 diopter, especially from Volk and other standard company. You always see the term double is aspherical. Why they use double aspherical? To correct spherical aberration. Without double spherical, you see the retina, but it's not good, not at all. So that's why that big companies has created double spheric lens of 90 diopter, 70 diopter, 20 diopter, and they work so good. And one of the reason why you see double aspheric there, not just one surface aspheric but both surface aspheric, because 90 diopter is huge power, isn't it? So in finally, paraxial assumption, where spherical surface and paraxial rays are so important for sine theta is equal to theta when theta is radiant. It's very important to understand. In case of spherical aberration, just remember one thing: peripheral rays focuses closer and central rays focuses away, and that's where spherical aberration lies. There is many more things that is spherical aberration we have to understand about spherical aberrations. So about night myopia and how we will correct spherical aberration with a spheric lens, which is very good way. And even clinical recommendation is that greater than 7 diopter of spectacle, especially plus 7 diopter of or higher spectacle, we use a spheric lens, which is very good for field of view, for controlling aberrations, all things, especially in case of aphakic patients. So it's central important to understand about spherical aberration. Definitely I'm going to recommend this book for a start. Great book and all time of my favorite by Professor Dr. George Edimeris. See you soon with another video from coma to, I think, distortion. Let's see. Bis dann, tschüss.